So any questions about this particle in a cube? Any questions, comments? No? So let's look at something else. Let me remind you that for free particle we had E equals to p squared over 2m or h bar squared k squared over 2m. And when it's a free particle, right, you don't have quantization. It's not confined, so you can have any k you want. What if, and this is the case for one-dimensional free particle. What if you have something like this? This is very long. So it may be continuous forever for all practical purposes. So in x direction, so it's in a two-dimensional box in x and y, okay? But in z direction, it's infinite. There is no bound. What will be the energy for this one? Let me remind you, when you have three-dimensional confinement, there are corresponding three quantum numbers, right? Everybody with me? This time, there will be corresponding quantum numbers in x and y, so the energy will depend on two quantum numbers and the kz in the z direction. So the energy will be h bar squared over 2m times nx pi over a squared and y pi over a b squared plus just k squared, yes, kz squared. Say it again.
Is it like behaving like electromagnetic wave?
Sort of, yes. We have discussed this. Somehow, everything that you see in quantum mechanics is very deeply related to what you see in electromagnetism, right? So, what do you see here? You see these are quantum numbers, these are integers, and this other one is a real number, right? So the integers can have values 1, 2, 3. This can be anything between minus infinity to infinity. I wanted to mention this to introduce you to the concept of the bands, okay? Like when you have, let's say you have nx equals to 1 and y equals to 1. So you have some number coming from here, but on top of that you have kz squared. So if you are going to plot it, let's plot it kz versus energy. Okay? So this is, oops, let me use this value. This is what it looks like. So as you change kz, you draw a parabola, right? Now you can change. Do you have any questions at this point? So any point here corresponds to a certain solution to your problem. Okay? And each one of those points are solutions. Okay? Let's change. For example, what about nx equals to 2 and y equals to 1? Then it's another parabola That's a bit higher, but it's also a parabola, right? Like this. How about n x equals to 1 and y equals to 2? It's again a parabola, right? But on top of this one. So you have a degenerate band there. We call these things bands. Okay, and we will come back to this concept over and over again. Okay? So hopefully you understand what's going on with the confinement and extended states. Do you have any question at this point? Any question, comment, idea? We didn't play with the tunneling code. We did see it once, but we didn't play with it. So let's play with it a little bit. So what do I have here? I have some energy, right? And I have a potential barrier. Let's look at the potential barrier. The height of the potential barrier is 20 electron volts, and the thickness is 1 angstrom. So let's see if the electron goes to the other side or not. So this is our electron traveling through, right? And we have constructed this by putting together several momenta, right? So you can see part of it goes to the other side and part of it reflects. And if you indeed take the integral of this part that goes to the other side and compare it with the formula that we got, you will get a close comparison there. I used to give it as a homework. I don't anymore, I guess. So what will happen if I increase the thickness of the barrier? So height is the same. Do you see that the thickness is visibly increased? Do you see it here? The thickness. What do you expect? Yeah. Yeah. You can see much less of the wave is passing through to the other side, right? 0.4, what will happen? What will happen then? Say it again.
If the potential barrier is direct alpha,
What happens?
I don't remember.
Can we solve it? Please solve it and tell us. Do you see much more of it passes through? Okay. So we have played with the tunneling code.
John, when they become the same, is it when it's 1?
It is when the transmission is half. Okay. To transmit fully, then we need to have a very thin barrier. Okay. It's not even seen in the figure, so.
I just see in the figure 3.0.
What?
Actually, maybe it's not resolved by the fluid.
Yeah. A bit thinner, so let's see. But still, classically, it shouldn't be able to go to the other side. Okay? Classically. What?
Hocam, is there a threshold for the barrier that we can calculate for the electron cannot move to the other side?
There will be always a probability that it moves to the other side.
But the probability is going to less unless the barrier.
Yeah, yeah. So, by the way, we didn't talk about radioactivity, maybe. So, I should have reread that part, but more or less, if you remember that part, please remind me. If I'm doing something wrong, please correct me. So, as far as I remember, once we have this quantum mechanics and stuff, there is this famous potential that describes radioactivity. So, beta decay, I guess. Like, there is an electron that wants to escape, but there is a potential barrier in front of it. Maybe, maybe not. I remember, can you check this one? Gamma radiation. Okay, so it oscillates basically here, and there is some probability of passing through the potential, tunneling through. And they put together this oscillation and probability of passing through. So it's sort of like this tells you how many trials of the electron, how many times the electron tries to escape by tunneling. And if you multiply that with the probability of tunneling, you basically get some expression for the radioactive decay.
For beta radiation, there is no electron inside the nucleus.
You just check it out. Okay. Did you check this name? Check why you are coming to the classes. Yes. Okay. So the next thing is very important. So let me give it a try. The next thing is the most real thing that we are going to do, which is hydrogen atom. So, let's think about it. Time-independent Schrödinger equation for hydrogen. How does it look like? Well, if you remember, we said that del squared over del x squared plus del squared over del y squared plus del squared over del z squared was this. Do you remember this? So it has some expression in spherical coordinates, right? But I wrote a code that still does this one. So I will show you that. Okay? We will not solve it actually analytically, because that's out of the scope of this course. But in general, you can write down time-independent Schrödinger equation like this. So you have this part, and then you have the potential. And the potential looks like this. Let me not use k, maybe it will be confusing. 4 pi epsilon 0 e squared over r phi equals e phi. Do you remember why we have this ER? Can someone explain me? Yes, so it's like a proton in the middle, and at a distance r there is an electron. What should I write? It has a charge plus E. So is it confused with this? Anyways, this is proton, okay? And it has a charge plus E. So the potential between these two are ke squared over r with a minus sign, which is 1 over 4 pi epsilon 0 e squared over r. Do you remember this from Physics 102, hopefully? Yes? Good. So we already have Bohr's model for this, right? Bohr's model gives us some value, and this is what we get. Interestingly, when you solve non-relativistic, sure,
It's E squared or E? KE squared or KE?
it's E squared because the potential is K times Q1 times Q2 over R. Okay?
No, it should be Q Q1 divided by R. Yeah.
That's actually correct.
Potential energy is charge squared.
Yes, and this is potential energy. Okay, then there is a confusion here. You are right that when you are doing physics 102, you write potential as V because of the volt, right? But what we are writing here is potential energy. Okay? Yes. Do you understand it? So this is the U of the physics 102. So, and Q1 is, let's say, E, and Q2 is minus E. Okay? When you solve non-relativistic Schrödinger equation, surprise, surprise, you get the same value. Okay? So Bohr's model was actually really, really successful. But when you add relativistic effects, which we will not do, you get something called fine structure. So, for example, we basically get in Bohr's model and in non-relativistic Schrödinger equation, we get 1s state, and then there is all these 2s, 2px, py, pz. They all have the same energy. Okay, we will see this in a moment. So somehow we do get 3 quantum numbers when we solve this equation, but energy depends only one of those quantum numbers. Are you following this? But when you add relativistic effects, then these energies go up and down. I guess this one goes down, this one goes up, right? What are these relativistic effects? For example, there is spin-orbit coupling. Spin-orbit coupling. But we haven't talked about spin yet. So that's one effect. What was the other one? There is this lamp shift. Yes. Some effects. Okay. So how can we solve what I want to demonstrate to you today is that you can actually solve hydrogen atom in a computer, and it will give you a fine result. Okay, I have the code over here, and I want to go over this code really quickly, if you will allow me. Remember how we solved del squared over del x squared? So we had something like fx plus delta x plus fx minus delta x minus 2fx over delta x squared. Do you remember this, everyone? We had some Hamiltonian and it depended on it like this. Well, now we have this one. Then we have to have all these things and then others, right? Minus plus delta x, delta y, plus fy minus delta y, plus fz plus delta y, delta z, plus fz minus delta z, minus 6fxyz, right? The central point, divided by, let's say every direction is the same, let's say. I will explain it better soon by this drawing, okay? So let's say you have a grid, and this is the central grid, right? That's the central grid. Then you have minus delta x plus delta x, right? Minus delta y plus delta y, and minus and plus delta z, right? You are basically calculating the curvature based on this. So far, are you following? Yes? So once you have that, if you remember, once we plugged in this Hamiltonian, the Hamiltonian for the 1 dimensions would look something like this. For the 1D Hamiltonian would have this minus 2, 1, 1, 1. That was the kinetic energy, right? Do you remember this? Yes? Which would correspond to just 1 dimension. We would discretize this in 1 dimension. But this time, we are discretizing in 3 dimensions. So there will be like minus 6's here, dot, dot, dot. And then there will be several ones, actually exactly 6 ones on some other places, but there will be some zeros in between. Now, why is that? Because this part is really hard to grasp if you haven't coded this at all. The point is that you are basically discretizing it all over the place, right? And you are giving some numbers to these discretized points, like 1, 2, 3, 4, 5, 6, 7, 8, etc. Sometimes the neighbor of 3 is not 4, sometimes it's 7. Do you see what I mean? So sometimes those ones appear at different places. So what this code does is the following. So it's h bar, just we talked about, me, mass of the electron, and this one is k times e squared, like k is the 1 over 4 pi epsilon 0, 1, okay? And this is expressed in terms of these units, okay? Then there is a box which is 30 angstrom, 30 angstrom, 30 angstrom, like that, a box. And each side of the box is discretized into 100 points. So how many points do we have? 10 to the 6, which is 1,000,000, right? So we have 1,000,000 points to solve. So what is the size of this Hamiltonian?
3 million by 3 million.
Why 3? We have 1,000,000 points.
Ama ikisi yer için ayrı ayrı alıyorsunuz.
No. That's the thing. Like the 1,000,000 points are distributed in X, Y, Z. We name them first point, second point, third point. You go in X, 100, and then you go down in Y by 1, and then 101, and etc. And then when you reach 10,000, you go 1 in Z and 10,001, 10,002. Do you understand? So it's like that. So million points in total. So your Hamiltonian is million by million. Okay?
Do we have
Tiny.
I mean, isn't it a problem to save that kind of matrix?
Very good point. It is a problem. But what we do is, yes, we use sparse matrix. Do you know about it?
Yeah, 99% of the matrix is 0.
Yeah, exactly. So most of the matrix is 0. That's why, so as you can see, actually, even more than 99%, because look, this is 1 million points,
We have only 6.
and only 6 of them is non-zero. Okay? You actually have to only save 6 million numbers. Because million lines, each line has 6 values. All right, how do we do that? We basically save the indices and the values, okay? And then once you do this, sparse IJV, indices and values, it creates that sparse matrix, okay? And it doesn't take that much space. What happens next is you are solving it, you are doing this eigenvalue solution. Yes.
Can you just try to write like zeros 1 million by 1 million just to see how much space it takes? Because it shows an error that it says I need that much space, so
Okay. By 10 to the 6, right? Yeah.
it gives the amount in
It's, you need 7.5 terabytes. Okay? So, much better to do it in a sparse, I mean, much more possible to do it like this. Tell me.
It's 7 terabytes, yes?
7 terabytes, yes.
and it not an SSD space, it should be
RAM spaces.
Yeah, very good. So we solve it. V and D will give us the eigenvalues and eigenvectors. Yeah, let me show you how it solves. So it defines it very quickly and it starts solving very quickly. Okay? But let's not wait for it. Let's just clear everything and load this one because we have done this before and we have saved it, right? And this part should actually plot it. Okay? Do you see? This is a pi z orbital. Very cute. Let's go for 14. Okay, not what I expected. 13, number 13. Let me go back and start from, which orbital is this one? This is d orbital, right? The thing that you have seen in chemistry books all along, right? It's just the solution of Schrödinger's equation in 3 dimensions. Okay, so let's look at the energies. It starts with almost 13.6. So why we are not exactly 13.6? Yes, so if you increase the precision, if you put more grids over here, like maybe this is still 30, but you put it to 200, 1000, whatever, okay? Then you will approach 13.6. And what is this one? What is this value? 13.6 over 4. Actually, that one is better approximated. So it's supposed to be 3.4, it's 3.44. It's better approximated because this one is 1s orbital and it's rather small, okay? 1s orbital. Let me plot it actually. Is it boring, by the way? No? Are you sure? So let's plot it. So this is a tiny 1s orbital. And since we are using an equal grid everywhere, so it's less precise for that orbital. Does it make sense? How?
We are using equal grids, so
Yes. So
Py and Pz is not much symmetric than the 1s orbital. So
no, look, let me tell you.
if you think about the number of grid points inside an orbital, yes.
Like I am taking a grid like this.
You cannot see this.
I'm taking a grid like this, let's say, and the 1s orbital is like this, while the pi orbitals are like this.
It's like number of grid points per orbital.
By the way, just something else. This is still hydrogen atom in a box because my program actually sets these boundaries to 0. Okay, hydrogen atom in a box. But if you want to improve actually the s orbital characterization, you can increase the grids, or you can actually decrease this one. You can put it in a smaller box, then it will see the s orbital more nicely.
What happens if the p orbital is outside the box?
Very good question. They are not. they decay enough. Yes, they are a little bit squeezed. So let's look at, for example, number 2. Number 2 looks like this. So this is if you can compare, it actually drew it on top of the other one. So this is 1s orbital, this is pi orbital, okay? Of course, what I'm drawing is an isosurface. So let's see what I'm drawing. I'm taking the maximum of the absolute value, and that is Fc, okay, of a certain wave function. And then I'm drawing an isosurface where Fc, the function is equal to Fc over 3. That's what I'm drawing, okay? So this is the second one. The third one is this, okay? Let me draw the second one again on top of this one. It should be orthogonal to each other. Do you see that one is directed like this, the other one is directed like that? Let me also draw you the fourth one. And that's directed perpendicular to those two. Do you see it? Like this. So it's pi x, it's px, py, and pz. All right? And the fifth one is 2s, I guess. Yeah, the fifth one is 2s. Sure.
In the energy levels, and the second energy surf and force is related to the p orbital, and the fifth one is related to the s orbital, but the fifth one should be less than the p ones, not greater.
Yes, actually it should be exactly equal in this theory.
Yes, since there is no electrons in that orbital.
No, not because of that. Just they are these values, this one, and this one, all four of them should be exactly equal to each other according to the level of the theory that we are solving, okay? But they are just a little bit different because of numerical thing, okay? But otherwise, if you have perfect grid, if you have infinite space and stuff like that, they are exactly equal. So, yes?
2s is greater than the 2p orbitals.
In energy, you mean? When you include relativistic effects. Do you see my point?
But in reality, 2s fills with the electron, d for the 2p orbitals. We fill the 1s and then 2s. And
Yes, so 2s has lower energy.
Lower energy, but in this.
Yeah, this is just numerical mistake anyways. Could have gone either way. Like,
The energy level in these rows are kind of wrong.
Yes, yes. And then, what do you expect next? So, what this one tells you that, so you have 1s at a certain energy, which is 13.6 minus. Then you have 2s, 2p, x, py, and pz, which are all at 13.6 over 4, okay? And then the next one is 3s, 3p, x, py, pz, and then do you remember the things? X squared minus y squared. Do you remember the others? xz, yz. Yes? So how many in total?
5.
Yes, 5 of this, 3 of this, and 1 of this gives you 9, right? 9 orbitals that are 13.6 over 9. 4 orbitals that are 13.6 over 4. 1 orbital that is... And you can see this in the solution as well. Do you see? They are very close to each other. I didn't have a chance to draw my favorite one, so let's look for it. Yeah, this one. Isn't this beautiful? I think so. Right? So all this is just a solution of the Schrödinger's equation, and it just spits out these energies. And if you do the whole solution, you will see that the wave functions, as we can see here, depend on, so the wave function depends on n, l, and m, okay? So 3 quantum numbers, because it's quantized in 3 dimensions, right? But energy depends only on n, and it's minus 13.6 over n squared. Okay? Do you have any questions, comments?
For other atoms. For other atoms, helium, argon.
What do you want to know for other atoms? You cannot solve Schrödinger's equation for even for helium? No.
So the quantum constructed for hydrogen atom, then they produce this theory, and then we fill the orbitals just like our imagination.
No, there is no like closed form solution. You have the solution, but there is no mathematical formula that corresponds with that solution.
Yeah, so you can solve it in a computer. You can solve it.
Navier-Stokes equation. Navier-Stokes equation.
Exactly. The problem with Navier-Stokes is more mathematical. Like, you are just, I don't know why you bother yourself with existence. Who cares if there exists a solution or not? Yeah. We will come to the problem with many electrons. So we will start this next week. We are doing review, right? But then afterwards we will start talking about more than one electron, because once you have helium, there are 2 electrons, and all hell breaks loose. Okay.
And that orbitals, for example, 2s with 2 pi's should be different in energy.
Yeah, we are lucky that they are still a good first order approximation for other atoms as well. Yes, all hell breaks loose, but there is still some orbital theory that is there. Like we can just simply put electrons into those hydrogen-like orbitals and understand the atoms to the first order. But if we are interested in detailed stuff, exact energies, exact wave functions, and things like that, then you have to go further. But as a first approximation, hydrogen orbitals are like hotel rooms. So if you have 2 electrons, you just fill in the first orbital with those 2 electrons, and then you move to the second floor, and you continue like that. And those mishaps that happen, like for example, before filling 3, you have to go to 4s and stuff like that. Exactly. So all those can be explained by doing calculation.
But for example, for Cooper atom,
Mm-hmm.
one of the electrons from the s orbital moves to the d orbital.
Mm-hmm.
It's the spin orbitals.
Yeah, but I wanted to ask, who found that? How can they found that? For example, this electron is located in that orbital, not this orbital.
Okay, your question is how we figure out where the electron is.
By experiment.
We figure it out by our theory together with experiments. So for example, we say that it must be in a d orbital because it's, let's say magnetized or something. Like I'm actually measuring some magnetization there, for example. Okay, so it has to have some effect that we can measure, and then we can go back to our theory, and those two should corroborate each other. Okay, like ultimately what I am doing, for example, I'm putting, let's say, carbon atoms together, okay, finding the distance where the carbon atoms would sit together. Let's say I get 1.5 angstrom. There's an experiment. I don't know how they might measure this, but they get 1.5 angstrom as well. Okay? So we will first face the many body wave function problem. Then I will briefly talk about density functional theory. And once you have density functional theory, you go back to problems being simple. Okay? Using that and good algorithms and computers, you can actually calculate even materials that don't exist in nature. Okay? All right, let's stop here.